we tried this. So I don't know if you can click on it. There we go. You're good now.
Okay. Okay. All right. So purpose of this talk is to basically just give you an overview of fire ecology. As I mentioned before, fire ecology is essentially anything and everything having to do with the interactions of fire and the environment, natural environment generally. I'm going to start with talking about describing fire regimes, which is sort of a broad category. We're going to look at some of those effects of landscape and broad scale fire effects. And then I'm going to spend just a little bit of time talking about stand level effects. The fire regimes essentially are a generalized description of the role of fire in an ecosystem. They're based on a number of characteristics. All of the fire regime systems share in common some level of disturbance, fire as a disturbance, the dominant vegetation type, and the fire severity, and the interactions, subsequent interactions or results of fire in that ecosystem. Generally speaking, fire regimes in the warm, dry environments, the lowland environments, historically, I shouldn't say historically, the fire regimes operate in a low severity classification. So fire, when it interacts with these ecosystems in a naturally functioning fire regime, when it interacts with these warm, dry ecosystems, it has low intensity and is generally beneficial to that forested or to that ecosystem. As you move up in elevational gradient usually, but into cooler, moister, more productive sites, that fire severity tends to get more and more higher and higher in terms of the amount of severity and the impact of an individual fire on the ecosystem. But fire, regardless of how we classify them, fire plays a role in all of the ecosystem types. It's just mostly a matter of scale and severity of the resulting fire. So high severity fire regimes, we kind of already covered some of this, but high severity fire regimes typically have high intensity surface fires and can result in group torching, individual tree torching, group torching, or crown fire. And they tend to be high intensity, so trying to put them out is usually quite challenging. And on the landscape, they essentially are predominantly stand replacing. Most of the scientific definitions revolve around this idea that if 70 or 75% of the dominant basal area, overstory basal area is killed, then it's a high severity fire or a high severity condition. And this is an example of a high severity ecosystem where you can clearly see that the younger, more dense trees to the left, that's an old fire scar. And for whatever reason, whether it was suppression or something else, as it crept over that little finger ridge there, it basically went out or turned into a non-stand replacing fire. And based on this ecosystem and where it's at, it probably just went out due to snow or other factors. Moderate severity fire regimes, on the other hand, tend to only kill between 20 or 25% and up to that other window of 70 or 75% of the basal area of these stands. And so it's really a mixed condition, a mixed bag of effects. And so you get these patchy sorts of stand replacing events. These sometimes larger patches of stand replacing events, but then you get these little tiny isolated mortality patches, down in here or here, where it's a much smaller patch of stand replacing mortality, and that's a hallmark of a mixed severity fire regime. And what they tend to look like a year after, when all the crowns have died, is something kind of like this. You'll have some stands that have been completely, or some individuals or patches of individuals, like in the foreground, that have been completely consumed, killed right off the bat by the fire. But then for a full year out, we call them secondary fire effects. You'll get these other groups of trees and individuals out here in the distance that die. They succumb to their either the damage that they incurred from the fire directly or from secondary agents like beetle mortality that come in the following year and will finish off the already weakened tree. So low severity fire regimes then are essentially fires where you don't have any stand replacement, very little, 0 to 25, use that number, 0 to 25% of the overstory gets killed in any individual fire. And this is a great example from 1909, what some of these conditions look like. And that same stand, that's, I mean, this is not the follow-up photo to that, but those stands persist through time. There are mortality agents that and processes that will kill off these groups of big, large pine like this. But it's a totally different dynamic within the ecosystem, within these low severity fire regimes. That essentially the majority of mortality happens in small patches, either as a result of competition and insects and disease, or it happens as a result of some ingrowth that is able to establish underneath the trees. You can see a little bit of that here. And those trees, at some point in time could be susceptible to a small patch of mortality. Everything else would be surface fire. But what we're seeing in contemporary times is that these fire regimes are changing, and it's most easily communicated, I should say, with the example of ponderosa pine ecosystems. These warm, dry systems aren't super productive, but they're productive enough to build up understory. After 110 years now of fire suppression, and succession happening in lieu of fire suppression, or in conjunction with fire suppression, you go from these relatively open stands to these really, well, quite dense stands. I won't say really dense because you guys are on the west side. But these conditions, essentially, all those trees, all those little trees have established since the last disturbance, which, for sake of argument, let's say it was 100 years ago. All those trees are 100 years old versus that big yellow pine to the right there, which is probably 300, 400, or 500 years old. It has survived numerous fires, dozens of fires, and more than it has survived dozens of fires. And these other trees haven't had any fire to them whatsoever. And so, successionally speaking, and within the stand, what happens is these things grow up. Not only they create more hazard for these old mature trees when it comes to fire, but they also stress those trees by pulling creating competition for growing resources. So they shade things out. They take up water. They attract beetles. And a lot of times, most of the time, these smaller trees are not fire adapted. So oftentimes they're what we call shade tolerant trees, which means that they can grow up under lower light levels of that ponderosa pine overstory. And at the same time, they're not fire adapted. So when a fire comes through, these trees will be killed. If you're lucky enough to have maintained your old mature fire adapted trees like that ponderosa pine, if you're lucky enough to have maintained that, when these trees that have died fall down, they will be a super high severity fire when another fire comes through that area. And so it's an accumulation of biomass that's creating many of our issues in the Western United States. And it's not something that can be easily worked out of. So within ponderosa pine stands, with most ecosystems with ponderosa pine are able to support Douglas fir, which is relatively fire tolerant itself, and those two tend to coexist. White fir and grand fir, though, are both fire intolerant species, and they are extremely effective ladder fuels, and they do not do well with fire. So these changes in ecosystems are occurring across broad landscapes. I guess I'll start on the right there, and just basically the lighter colors. So the light yellow. The light yellow is areas that became a low severity fire regime or low severity predicted fire behavior. The orange, bright orange, are the ones that became mixed severity, and the red ones are the ones that became high severity. And on the bottom row there, the kind of the off shades of yellows, orange, and red are the ones that remained, they were already in that condition. And what you can see here, though, is that a lot of the interior Columbia Basin, is essentially what this is, the Columbia Basin, for the most part, has converted to mixed and high severity fire regimes as a result of fire suppression. And on the left, what you can see is one of these study areas that there's 300 of them throughout the Columbia Basin. But you can see on the top row is the historical conditions. In that first column is structure. And you can see how the structure has simplified in the second row. So diagram A there is the historical forest structure as it was mapped in the early or late 30s. And then diagram B is how it looked in the late 90s, early 2000s. And you can see in all these cases that these landscapes had gone from diverse conditions to homogeneous conditions that promote fire behavior. And so diagram A is structure. Diagram C is fuel loading. So that's the amount of fuel that's on the ground. Diagram E is the crown fire potential as a result of ladder fuels and surface fuel accumulation and the predicted likelihood of crown fire to occur. And you can see that that's greatly increased in diagram F. And then the last column there is flame length. And that's essentially saying that you've gone from a diversity of flame lengths, surface fire flame lengths, to mostly high, very high, which, if I remember correctly, was 8 to 10 feet flame lengths as a result of fuel accumulation and changes in fuel types. So these conditions are changing across the Western United States, and they're thoroughly documented. But as I mentioned, they're not easy to work our way out of. This is a historical picture in 1934 from Mission Peak. On the top there, it's from an old fire lookout. And in 2010, a photographer went out and repeated those photos. And what you can see is the amount of ingrowth that's happened. You know, on the top there, there's all kinds of open areas, open spacing between trees, meadows up on the top there, and the top of that nearest ridge in the foreground there, and down, down into the lower slopes. What's interesting about these pictures is not only the ingrowth and the changes between them, but if you look in the bottom picture, just out on the toe of that slope, sort of in the middle of the picture, you can see there's some orange trees. And those orange trees are stressed trees because look where they were growing, what kinds of conditions they were growing in 1934, and look at how many trees are there now. And that's a result of soil and ecosystem processes that do not align. Those trees did well enough to grow up together and to forest that, but because there's been no disturbance to maintain that as an open condition, you basically have trees that can't be sustained. And what's going to happen to those trees is they're going to fall down, die, and eventually fall down and become surface fuels that will potentially impact the soil and what was formerly an open shrub or grass opening. And another example from the Eniat watershed just south of Lake Chelan, from Duncan Hill. Same story, different ecosystem. This is a more productive ecosystem. But what's interesting about this is in the top picture, you can see all of those fire scars. And you can see how frequent or how often fire occurred on that landscape. Those are all different cohorts of fires that occurred. And contrast that to the bottom, and you look at the trees that are there now, and they're all essentially one age. But again, of interest to me as an ecologist is the fact that areas that looked like they were probably non-productive in the past are having some serious issues in terms of maintaining themselves in contemporary times. So high intensity fire, as I mentioned, stand replacement is common. This is a primarily lodgepole ecosystem, lodgepole and larch up on top of Table Mountain, so near Mission Ridge or Blewett Pass, from the 2012 Table Mountain fire. And this is what a high severity fire regime looks like. It's important to point out, though, that not everything is stand replacing. And so these green trees here in the middle are going to be the seed source, potential seed source for the areas around them. Lodgepole pine, we'll talk about a little bit more. It doesn't necessarily need a seed source. These are actually subalpine fir. But these subalpine fir will help reseed these non-forest or these stand replaced conditions out here. And so it's really important that there's variability and variety in how fire behavior happens. And that was how fire controlled or interacted with ecosystems. There was this constant shifting mosaic of fires occurring. And so you didn't always have the same patches stand replacing and creating homogeneous forested ecosystems. You had variability. You had different ages of trees. You had different accumulations of fuel and different fire behavior. The mixed severity fire regime, again, looks like this, right? So this is larch and lodgepole understory on Table Mountain, and you can see how these patches look much different than that last slide, right? There are individual trees even within the green, what would be primarily green areas. There's individual trees that have died, but there's a sufficient amount of growing space that's been opened up for this larch lodgepole ecosystem. And larch and lodgepole will duke it out. If the conditions are right, essentially larch will take advantage of it. But with the way that lodgepole regenerates itself, it can be a really hard battle for larch to establish itself. Again, the importance of these refugia or these green areas to reseed and promote forest development in these stand replacing areas is important. And these tend to happen in the mixed severity fires tend to happen in these mixed conifer zones. The last one was a subalpine fir ecosystem. This is a larch or lodgepole mixed conifer ecosystem. And then these low severity fires, this one is a more of a fuel limited example of low severity fire. You can see all those open areas that didn't burn, and that's because they didn't really have any fuels to move between. But where they did, or where fire was able to spot into a new area, you just had primarily surface fire. But if you look just above that road down there in the bottom portion of the picture, you can see how even low severity fire plays a role in thinning up the bottoms of tree crowns and reducing understory. Those trees are likely to die and create growing space for the larger, more mature, and more fire tolerant species. Another example of a, well, depending on how you define it, depending on how you delineate it, this is a mixed severity condition, or maybe a high severity patch within a what's typically a mixed severity ecosystem. So fire effects are driven by topography and terrain and fire behavior and fire weather. And it's important that you have an understanding of them. And by no means are we good at predicting them. But what we are able to do is look at individual ecosystems and characteristics within stands and understand the likelihood of that stand or that ecosystem, the likelihood of it to persist through fire based on the conditions of the particular stand or the place we're looking at. This is another example. This is more of a fuels, but also you can see the influence of topography on this particular example, where you had some uphill runs that kind of nuked out or torched out those trees and killed those patches of forest that were on a more northerly aspect than what we're looking at, or sorry, more northerly aspect than the ones to the right, which are on a southerly aspect. And these kinds of effects happen. That's typical of north versus south aspects in ecosystems. It's just a cool picture. No, again, it's just another example of how fire varies across these landscapes, and an even better example of individual trees being killed by the by the fire, the first or second order fire effects, and then all the trees that survived. And again, primarily low severity fire. You can see individual clumps and shrubs that survived as a result of fire burning around them. And here's some within stand effects as well. Ponderosa pine stand here on the Okanagan Wenatchee. There's larch back there in the background. But you can see how patchy it is. There's some grasses over there on the right-hand side that are that survived the immediate fire. There's some needle fall. This is actually in the fall, of the same year. So there's some needle cast that as a result of that ponderosa pine taking some scorch damage and dropping some of its needles. But all in all, this fire or this stand is resilient to fire because they're fire tolerant species. It was low severity fire, and there wasn't much, if any, ladder fuels. Well, there's none in this scene that I can see. Another example of within stand fire effects, ponderosa pine stand, patchy burning. You can see that little bitter brush in the foreground there. There's some ceanothus right at the bottom border of the picture. So low severity fire regimes have a lot of variability within them, but generally speaking, they don't replace the stands. So as these stands recover from fire, you start to see more and more of this needle cast. You'll see a little bit more mortality from a typical stand. I wish my pointer worked correctly. Oh, wait, there it is. 1 second. Hopefully you guys can see the laser pointer here. Back here in the background, you can see a ponderosa pine that's taken some pretty good scorch. And it's, it may or may not survive that. But again, they're a very fire adapted tree. And what you don't see is complete consumption of the needles in any of these. And you also don't see any really significant scorch along the boles of the trees. This is a great example. This is a repeat visit to a photo point looking at the 1994 fires on the Wenatchee, Okanagan Wenatchee National Forest, just east of the Cascades here. And 1994, that's immediately post-fire. You can see that big tree. Up here, you can see where that tree was felled, more than likely because it was a hazard tree or was going to come down on somebody. There may have been, there was not any salvage logging in these photos. So this would have been brought down either by a firewood cutter or by somebody who was trying to prevent that tree from falling on somebody's head. But what you can see is all these trees back here, bark is flaking off. You've got some snags of smallish, but decent size. And then you've got this shrub component coming back in, and grasses. Oh, geez, that's 2003. 1996, I apologize. 1996, you get these grasses coming in first. There was some rehabilitation back in the 90s post-fire that did a lot of reseeding. So that's where these grasses are coming from. They typically take 2 to 3 years for grasses to start recovering in a normal system that hasn't been reseeded. But ultimately what happens is you get a fairly heavy shrub component as basically these things come in and colonize, and they start adapting the soil to be, they start fixing nitrogen and preparing the soil and recovering. And then they continue to grow. And right here in the foreground, you can see another ponderosa pine starting to pop up. And here's one back here in the a little further back. And you can also see that some of these trees have, some of these trees downslope have actually started to respond in a positive way. 15, 20 years later, they're starting to do pretty good in terms of they have growing space. They have no competition. They have no constraints on their crowns. So they're starting to recover and produce as, become mature trees. This photo didn't turn out quite the way I'd hoped to in this presentation, but this is up right off Blewett Pass, and I was intending to show some mixed severity fire effects. So we've gotten up into larch subalpine fir, larch lodgepole pine and some subalpine fir down here, some subalpine fir. But you can see sort of this mixed severity of conditions, and you can see how the fire kind of blew its way this way. And then it also made its way up the side of the slope, but it left this big wedge of green trees back here. And these fires, when they burn in these ecosystems, the Table Mountain fire was in 2015, if I remember correctly. And this is what happens with these lodgepole systems: is you end up with lodgepole pine, which not only has seeds that have dispersed, but it also is a serotinous cone. So it actually requires fire to melt the resin and release seeds. So there's two different functions happening with lodgepole pine. And you get these really dense stands that start growing up with this really heavy fuel load above it. And this is how that mixed and high severity fire regime perpetuates itself, and also how the ecosystem responds to that fire. So it's a really useful mechanism, and in some ways lodgepole pine is kind of an advantageous weed when it comes to forestry, because it's so good at colonizing and reseeding or growing before other species of trees can. So I'm going to throw some terms out at you. These are related to some other terms that we've talked about. I'll tie them together in a second. Residence time is the length of time that a flaming front is present. So a really slow moving fire, or a fire that's got really large fuels on it, will tend to move slowly, and it will tend to have quite a bit of fire intensity associated with it. Fire duration is the total heat received in all phases of combustion. So for a particular spot on the ground, or a particular square foot on the ground, fire duration is a measure of when that started burning. There's different rates of combustion where you see the flame, and then after that combustion, that flaming combustion, then you have smoldering combustion, which is the fuel is still breaking down, it's still burning, but it's not a flaming combustion. And that whole time it's generating heat and impacting its surrounding environment. And we'll talk about that a little bit more when we discuss soils. And then fire severity, as I mentioned, is really just the effects of these different fire intensities. It's the effects of the combination of fire intensity, fire duration, and residence time. And I threw this in here to try and tie it together a little bit, but it also describes fire behavior from a fire suppression standpoint. So these different shades of gray are different flame lengths of flaming fire. And then you can see that as the rate of spread comes down and gets lower and lower, for a given flame length, you can see how the amount of energy that's being released per unit area increases significantly. So if you have a 4-foot flame length, if it's like in a grassland and it's moving along at 300 chains an hour, or 5 miles an hour, it's moving really fast, but it's not a really high intensity fire because it's moving so fast. But if you have a 4-foot flame length in a timbered environment that's only moving it's moving really slow, you have all this heat and energy that's being radiated out from that flaming combustion. And it has relevance to fire suppression because it means we can't get very close to these things. And that's where these little simplistic diagrams are. Less than a 4-foot flame length means that we can use hand tools and be right next to it. Less than 8-foot flame length means we can use mechanical equipment, but we have to be at a distance from it. This means 11 feet or less is torching. And then less than 15 is basically stand back and watch it burn because there's not anything you can do. So it's called the hauling chart because it gives us an idea of what kind of resources we might want to have for a particular fire. Again, I present that only to give you an idea of how rate of spread, fire line intensity, and fuel load, or amount of energy, potential energy that's stored in a particular place on the ground, how those relate to each other. So getting into fire ecology a little bit more, and I'm running out of time, is adaptations of fire-dependent species. So there's species that do use epicormic sprouting, which is just sprouting along major branches or tree boles. There's underground meristems, which are where the growing material actually is protected underground. There's thick and fire-resistant bark. Doug fir's got thick bark that is somewhat fire-resistant. Ponderosa pine has fire-resistant bark. It just doesn't burn very effectively. So it protects the cambium of the trees. Thick needle clusters around meristems on branches. So the needles themselves actually protect the growing material, which means that won't get killed. Serotinous cones, I mentioned lodgepole pine. So that's an adaptation where fire's required, heat's required to actually release those seeds from the cones, and those rain down and post-fire recolonate with lodgepole in that case. Seeds, usually the high temperature requirement. Ceanothus is a great example. The seeds are released into the ground, but they don't become active and able to grow until they're actually activated by a particular temperature of fire. So the fire comes through a particular temperature, it activates those seeds, they reestablish. More easy to discuss is these general categories of plant responses. Invaders are a highly dispersive pioneering species. So these are the ones that take advantage of fire. Fireweed's an example, and salal, these two are great examples of species that invade after a fire. So that their response is, we'll invade that territory. They take advantage of it. Evaders are species that basically they just kind of duck when fire happens. I mean, the species itself disappears, but its offspring come back as a result of seeds being stored in the soil or in the canopy. Ceanothus and lodgepole. Avoiders are a good example as well, or sorry, another category as well. They're shade tolerant, and they really don't like to be in fire. And they aren't adapted to readily take advantage of reinvading the area. So they basically either they avoid fire or they end up getting killed by fire, and then they struggle to adapt or recolonize an area. Resistors, ponderosa pine is a fantastic example. It just rides out fires as best it can. In a naturally functioning system, that's really easy, but in these new contemporary ecosystems with fuel accumulations, that's much more challenging. And then endurers are species that have the ability to resprout from a specialized structure. This is, oh geez, I'm blanking. This is an example of basically it's resprouting from its the root collar right at the base of the tree. Oak is an endurer. Oak species are endurers. They rely on fire to, when the tree gets killed, the underground meristems or underground structure basically is able to put up a new sprout, and you end up with an oak tree that will develop right next to that same tree. Aspen's another example. Fire mortality is, it depends on whether the tissue is lethally heated, and lethality basically occurs at about 60 degrees Celsius for a minute. If the tissue is exposed to 60-degree Celsius temperature for a minute or more, it typically will die. So that's how we end up with crown mortality. Well, any mortality is that significant temperature is reached for a longer period of time. Crown mortality is affected by having dense versus open stands, the canopy closure, the amount of depth or depth of ladder fuels, canopy depth or ladder fuels. So if the surface fire has the ability to consume canopy, it will kill the tree canopy. Foliar moisture content is part of that, and then certain species are adapted and do really well. Ponderosa pine doesn't torch very easily. It's got its crown is high off the ground, and its needles are widespread. Crown scorch and crown consumption are good predictors of mortality, tree mortality, not canopy mortality. For bole mortality, it's about bark thickness and cambial kill. Basically, if the temperature can kill the cambium behind the bark, that's what will kill a portion of a tree and either create a fire scar, or if it kills enough of the cambium around the tree, it will kill the tree itself. Wounds and scars kind of add to the likelihood of additional damage being repeated or increased in subsequent effects. And as I mentioned earlier, there's secondary effects that can kill tree bulls. Bark beetles are the prime example. They come in and target these trees post-fire that are under stress and releasing a certain pheromone, and they'll end up killing off trees. Root mortality is associated with the depth of the roots and the duration of the fire duration in that location. The organic layers, like we talked about with ground fire, they can basically just cook those roots in place, and especially where the roots have kind of adapted and come up into more shallow soils or into more shallow organic layers. And soil moisture, the water content in the soil will actually add to the ability to transfer heat into those structures. A lot of the endurers do so by resprouting, and most of the shrubby plants, woody shrubs and herbs survive fire by sprouting from a specialized plant part. Some are epicormic, some are rhizomatous. They're stolons and dormant buds, but basically they basically take advantage of the fact that their mother plant has died, and all those resources then shoot into new sprouts and move on from there, grow up from there. Burn severity can affect these things. If it's hot enough and severe enough, you can actually, you can kill the plant altogether. Here's the example of oak and the one that I zoomed through that I can't remember the species. Apologize for that. Grasses tend to, there's annuals and perennials. Annual grasses basically are invaders, and perennial grasses are endurers. They basically, they have a, bunch grasses are a great example. The biomass on top of the biomass on top of the plant itself will get consumed by the fire, but the plant every year has the ability to regrow from the tissues at the root collar, and so it basically just puts up, it's okay with fire. Annual grasses, on the other hand, have to reinvade a site, so it's a function of their ability to propagate seeds into the area. Cheatgrass is a great example. It's something that is invasive. It burns very readily. It promotes fire spread because it tends to cure out and become available as a fuel before other grasses have gone through their reproductive cycle. And it takes advantage of fire by reestablishing faster than the native species. So it propagates the disturbance regimes. Seedling establishment and survival is obviously more important for some species than others. The germination and establishment depend on the seed banks and the dormancy and the microsites, and they can vary significantly. Iliamna is a rare plant that is a great example of, it requires, for its persistent, it requires fire on about a 10 to 15 year, 10 to 20 year cycle. If it's more frequent than that, it actually depletes the seed bed because the seeds are only last for so long. So if fire exceeds about 10 years, then the seed's no good before that. If it burns too frequently, there is a proportion of mortality that happens to the seeds that prevent them from growing. So there's sort of a sweet spot where if it burns too frequently, it doesn't regenerate as a population. And if it doesn't burn frequently enough, it also doesn't regenerate as a population. Lodgepole pine, we already mentioned the seeds and their ability to establish effectively. Animals are essentially avoiders. or evaders. They run, they fly away, they burrow into the ground to evade the fire, or they just simply don't make it out of the fire well. And lastly is just talking about soil. Fire creates physical and chemical changes to the soil that is actually can destroy soils. And that has long-term ramifications, because in order to regenerate a site, you have to rebuild those soils. So soil heating is a function of the soil depth, and it's been measured as high as 800 degrees Celsius within the litter layer. And this chart kind of shows how, as the fire, this blue line shows the fire passing and peaking out in temperature. And you can see that at about an inch and a quarter under the surface, you can see how this temperature profile peaks out, and then it sort of levels out through the different phases of combustion, and then it starts dropping off. So the more intense the fire is, the more peaked this is, this pink line, and the more damage to the soils that occur. And what happens is they become hydrophobic, meaning they actually repel water, and the soil bulk density increases after repeated or intense burning, because the materials and the chemical and mineral components of the soil actually break down as a result of the heat. And so the soil collapses on itself and becomes more and more dense, which has ramifications for anything trying to utilize that soil. And the chemical properties can be changed substantially. Different nutrients are volatilized, and some of the minerals can actually also change in form. The hydrologic, as a result of the soils being damaged, hydrologic regimes can get altered. Atmospheric smoke and quality can be impacted by smoke, and changes in human use patterns, very much so, right? When we have big fires, we don't get to use that landscape like we did for recreation or for other purposes. And for the sake of time, I'm going to stop talking and just bump on to questions and get out of the sharing mode, so I can say thank you to everybody. I appreciate it.
All right, so if there's any questions at this time, now's the time to do it. But again, thank you so much for taking time out of your evening to do this presentation. It was awesome to watch, and I appreciate it so much. And I learned so much from it too, so thank you.
Awesome. If there's any questions, or if you have any feedback, I'd love to hear it. Again, I appreciate the opportunity. This is my first presentation in easily a year and a half, and I want to say probably more like 2 or 3 years at this point. It's what it feels like anyways.
This is Max Prince. I just want to thank you. I'm the president and founder of Shadow. And as far as bog fires, yes, we've had bog fires out here, and they take months to put out, because the big risk you have is that the tree systems here are shallow rooted. And so the fire gets into the root, and then the tree falls over, and then it spreads the fire. So the fire department has to stay on it for a long time. But, you know, I think that fire perception of fire in forests really changed during the big fires over Yellowstone, right? You know, that because you have this conflict of, oh, it's a national park, we need to put it out. But then the natural functions of fire were not happening. That was well learned at the Yellowstone fires. And I went there several years after, and you could just see the resurgence of nature coming back, right? You know, and that was pretty impressive. Not that we want one here at Shadow Lake Nature Preserve, but but nature is resilient. So
it is, and Yellowstone was a turning point for fire management. You know, for ever since fire suppression began, there's been the argument in the literature about the importance of fire in these systems, but it was overruled by the predominant viewpoint in society at the time. And Yellowstone was the turning point when it came to fire management, the realization that there was a time and a place for these things to happen. And maybe we had been exacerbating that issue. The evidence was there, but fire policy began to shift significantly after Yellowstone.
Yeah, it's a tug at the heart to see it burn, right? You know, but at the same time, you know that if it's happening in the right ways, that nature will recover over a period of time. So
yeah, I stopped sharing my screen, but my question slide actually has a photo from the Bob Marshall Wilderness where they've effectively, for the most part, let fires burn over the past 100 years. And the mosaics and the patterns and the landscape are fascinating to look at. This may not be the best picture, but I didn't. Anyway, who's got the time and the mobility to get out in the wilderness, I would highly recommend it. It's to the Bob Marshall. It's amazing. Cool.
Well, thank you again for a really great presentation.
Thank you very much for having me, and I'm glad it was helpful. And yeah, if there's any other thoughts or if you'd like to do this again in the future, let me know.
Yeah, and I said it in the chat, but I just want to let everybody know I recorded this meeting, and so it takes a bit to upload up to YouTube. So I'll send a link out to this video tomorrow morning. So you can use it, James, for whatever you would like as well. So awesome. Thanks again for your time, and I hope you all have a great evening. Yes. All right. Well, I'm going to go ahead and end that meeting now, unless there's any other questions.
Nope. Thank you very much, Annalie. I'll be in touch with you on email.
All right. Have a great evening. Thank you.
See ya.
Bye-bye.